what we're going to learn about today is power series. Now, power series are things like this. And what this means is that for each individual x, we consider this particular series and try and understand if it actually converges. Okay? And if it does converge, then it actually gives us some number, right? So we're going to take some x, and then we form something like this. And whenever this series here converges, then we have a number, which therefore creates a function. X goes to this number. Yeah. So it's a way to create a new class of functions. And it's a class of functions somewhat similar to things we've studied already, because if we just have a finite sum instead of an infinite sum, it's just a polynomial. Right? And polynomials are very standard, very straightforward functions. Yeah? And as we've learned, whenever a series actually converges algebraically, you can do everything with it. You can do it with an actual finite sum. So it should be no surprise that whenever this thing actually converges, whenever we can make sense of this, then it's going to behave nicely. It's going to be something that we can do a lot of things with. So an example, let me write a sentence. This is a power series. So example. If we consider this, x goes to, let's start from 0, x to the k. This is a power series that we've already studied, that we've already seen quite a bit. Can you tell me for what x's this thing actually makes sense? For what x's does this actually make sense? What range of x does this make sense? What? Yep. So this converges. For x between 0 and 1. Yeah? So this thing actually forms a function. It's actually a function for every x between -1 and 1. Yeah. And we actually know what this function is. What is this function? What is this function? No, that's not an exponential function. We have a formula for it. What is it? So we start with k equals 0, so it's 1 over 1 minus x. Yeah? Yeah? So this is a function, and then we actually know what this function is. It's this thing right here. It's this thing right here. Yeah? And this is a kind of a hint of where things are going, because if we turn this equality around, then we have this. I'm writing exactly the same thing, except I'm putting it the other way around. So if we are interested in this function, then what this actually says is that we can represent this as this infinite power series. Yeah? And there's going to be many advantages to be able to represent a function as a power series, because a power series, we're going to find out, behaves in an incredibly nice way from many of the things we'd like to do. Basically, everything we can do for a polynomial, we can do for a power series in its range of convergence. For example, if we wanted to differentiate this thing, it turns out that in the interval of convergence, we can differentiate a power series just like a polynomial. We can just differentiate it term by term. If we want to integrate it, we can also integrate it term by term. So all these very difficult things we've learned about integrating functions become trivial if we can represent them as a power series. Yeah? So this is why we've learned all this stuff about series. so that we have this ability to actually represent functions as power series. And we'll later kind of study this in a topic called Taylor and Maclaurin series. This is purpose of setting up this machinery, because it turns out there is a wide class of functions we can actually represent as a power series, and then we can do many strong things with them that previously were either very hard work with difficult methods of with various whatever substitutions, whatever we had to do. If we have something like this, if we can write it as a power series, it now becomes rather easy. Okay, so that's where this is going. But we're going to begin with just trying to understand what power series are, become familiar with them, become familiar with the concept of their interval of convergence, their radius of convergence, and that's what we're starting off with this section. Okay, so ultimately, we're going to learn to represent a wide class of functions as a power series like this, where these AK will depend on the function, and this is where we're going to center the power series on. Okay, and the simplest example we know at this stage is that this particular function is representable as this power series. Okay. Let us do another example. Consider this thing. This is example 1. Look at this. The sum k is equal to 1 to infinity of n factorial x to the n. For what x does this converge? Okay, so the way to figure this out is to just consider x as some fixed number for the time being, and then see if for that fixed x, this thing, which now is just an ordinary series, actually converges. And we have the techniques to understand when a series converges. Yeah? So consider x to be fixed. And if we think of this as just being for some fixed x, then what we're looking at is just some particular power series. Sorry, some particular series, right? So if I just gave you this, it's just a series, right? If I didn't have an x, if I had a number here, then it's, then it's just a series. If I had like 3 or something, then it's just a series. Yeah. So forgetting that we have x, and just thinking this is a series, x is just some number, we don't know what it is yet. How would you test this thing for convergence? What's a natural thing to try? Yeah, the ratio test, because we have a factorial that tends to give us good information for the ratio test. What would your guess be about the convergence of this thing? Take some number, pick some number, and then ask yourself, does it converge? What would your guess be? That it doesn't converge. Why would you guess that? Well, it depends, right? So if we had any number bigger than 1 here, then for sure it's not decreasing. What about if we had x equals 1/2? Then this 1/2 to the n is decreasing, yeah? But what about the actual series? Do the terms decrease if we had 1/2 to the n? Yeah, indeed. So let's put it over here. If we have x equals, say, 1/2, then we're looking at n factorial 1/2 to the n, which is the same as n times n minus 1, blah, 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 all the way to 1. Do that again. This is 2 times 2 times 2, all the way down to here. So the numbers on the top are way bigger than numbers on the bottom. Yeah, so we wouldn't expect this to converge. See what I mean? Yeah, give me the thumbs up icon. There we go. And if we had, instead of 1/2, we had 1/4, then we'd have this, would have 4, 4, 4, and we still wouldn't expect it to converge. Because again, the stuff on the top is way bigger than the stuff on the bottom. And it keeps getting bigger and bigger as n increases. Yeah? So just looking at this structure, we would not expect it to converge. And let's check with the ratio test. So use ratio test. So we're considering x to be fixed, so let's write our terms are like this. They're just an is x to the n like this. So the absolute value of an plus 1 over n. What happens? We are going to have n plus 1 factorial x to the n plus 1 over n factorial x to the n. And we have a whole bunch of cancellations, right? This n plus 1 factorial we know is just n plus 1 times n factorial. So then this just becomes n plus 1 mod x, yeah? And in the limit, this tends to infinity, right? As n goes to infinity. So what we'd need for this thing to converge is that this thing would be less than 1. And if this thing is actually bigger than 1, it definitely doesn't converge, yeah? And this thing actually goes to infinity except when x is equal to what can x be equal to so that this doesn't tend to infinity? Come on. No, I mean x is fixed, right? We've just chosen it, so it can't move with respect to n. 0, yeah? 0. So unless x equals 0, then this thing doesn't converge, and this power series has no meaning. It doesn't converge. Yeah? So this power series, I mean, formally we can write it down, but it's a really boring one because it has literally no meaning unless we stick in x equals 0. Yeah? So power series only makes sense i.e. only makes sense if x equals 0. Yeah? So this guy that we saw before, this power series makes sense for a much wider range of x, right? It makes sense for every x between -1 and 1. Yeah? We meaningfully get a number out from this power series for every x between -1 and 1. Yeah? This one here makes no sense unless x equals 0. So it's a really boring power series. It's not very useful for us. Well, this one actually is useful for us. This power series represents this function perfectly well for every single x between -1 and 1. Yeah? Cool. All right. Let's do some more of this. Let's look at this thing. For what values of x does this series converge? Okay. Solution. All right, so we do the same procedure. We're going to take x to be fixed, so we just think of this as some fixed number, and then we let an be these things, x minus 3 to the n over n, and then we take absolute value. And what do we get? We are going to get n over n plus 1, and then there's the absolute value of x minus 3 to the n. Not to the n, to the power 1. Are you happy with how this works out? Give me a thumbs up if yes. Okay. Thumbs down if no. I'll add more details. Good. So if we do this, what happens? So this thing will just tend to x minus 3 as n goes to infinity, right? So if x minus 3 is less than 1, then the thing will converge. So let's draw a picture. So this is the real line. This is 0. This is 3. This thing says that the distance between x and 3 is less than 1. So this thing is 4. This thing is 2, right? So we would expect this to converge for everything which is between 2 and 4. Yeah? And we can double check this by just writing out what this means. So note that mod x minus 3 is less than 1. This is exactly saying that minus 1 is less than x minus 3, which is less than 1. That's exactly the meaning of the absolute value of x minus 3 is less than 1. Yeah? Give me a thumbs up if that's clear to you. Okay. And then we can just add 3 to both sides. So that's the same as 2 is less than x, which is less than 4. No, add 2, we're going to add 3 to both sides. So that's 2 is less than x, which is less than 4, like this, which is what we see right here. Yeah? So we confirm this picture with this bit of algebra right here. Yeah? So we definitely have that this thing converges for every number between 2 and 4. Yeah? All right, but the question is, for what values does it converge? So we know a lot of values for which it converges. What else do we know from this little calculation? Where do we know that it doesn't converge? Where the inequality isn't true anymore? Kind of. So if this inequality isn't true anymore, then it's not true that the limit of an plus 1 over an is less than 1. So if we don't have that, then logically, what do we have instead? What are the possibilities if that's not true? Come on. Perfect. Then either the limit n goes to infinity, an plus 1 over an equals 1, or the limit n goes to infinity, an plus 1 over an is bigger than 1. Okay, what do we know in these situations? Exactly, yeah. This is actually the ratio test. We are using the ratio test. At this point, when we just take x to be some fixed number, we don't think about what it is. We are completely applying the ratio test. You know? And in this case, this means that these terms definitely won't converge because ultimately each guy is bigger than the guy before, right? That's what this limit says. You know, after some large enough n, an plus 1 will always be bigger than the last guy. That's what we've seen, you know? So this thing definitely does not converge. This thing, when we have this thing, then we don't know anything because it could converge and it could not converge, you know? You know? Can you give me an example of things for which we apply the ratio test, for which the limit is 1, but it does converge, and then give me an example where it doesn't converge? Think about what the ratio test does. The ratio test is an X-ray machine to detect if a series in its bones is like a geometric series or going down to 0 fast in a geometric series. What series do we discuss that are nothing like geometric series? Telescoping series, something simpler perhaps? Come on, people. Yeah, so harmonic series, right, is an example of a P series. So you know it does not converge. And if we take the limit of an plus 1 over an. What happens? This is just n over n plus 1, which tends to 1, so we don't detect that it doesn't converge. Yeah? And if we change this slightly and then have the sum of 1 over n squared, yeah, this thing does converge. If we consider the limit of this thing, it is n squared over n plus 1 squared, which again tends to 1. Yeah. So for these p-type series, n to the p-type series, yeah, the ratio test is useless. It tells us nothing. These are behaving in a much more subtle way. You can't detect anything with the ratio test. Yeah? Which is why this case is important. It's just saying that we have no information here. Yeah? So here, no information. And then here, it diverges. Okay, so logically, we've broken the situation down into the case where the limit is less than 1, we know what's happening, it converges. And then there's two other possibilities. Either this thing, yeah, where the limit's 1 and we have no information, or this thing where it diverges. So let's write down what we actually know. So we also know that if x is strictly outside of this interval, so if it is between minus infinity and 2, yeah, where it's strictly less than 2, and it's between 4 and plus infinity, where it's strictly bigger than 4, then it doesn't converge. Yeah? So out here, that's an unfortunate line. Out here, it definitely doesn't converge. Let's write that down in language of maths. We know that if x is less than 2, or x is bigger than 4, does not converge. Yeah? As a consequence of this. Again, from the ratio test. All right, so have we answered the question? Have we answered the question now? Do we know everything? Have we answered the question, for what values of x does this thing converge? Come on, people, let's raise the energy. Let's get some more stuff going. Right, we don't know anything about 2 and 4. In this case, we don't know anything, right? We don't know anything. So when we have x is either less than 2 or x is bigger than 4, then we're in this territory and it definitely doesn't converge. If we have x strictly between 2 and 4, then we are in the territory where the limit is less than 1, and then it does converge, this territory. But when x is equal to 2 or when x equals 4, it definitely doesn't have any information for us what we've done. Yeah? That gives us no information. Yeah? This is a key point which we're going to have to use over and over going forward. The ratio test is only going to give us so much information. And that's the limit of all it will tell us. Yeah? Everybody happy with this? Yeah? So we have to do something for the case, because the question says, for what values of x does it converge? We can almost answer this question, but there are two values of x left where we don't know the answer. So what should we do? Well, the only thing to do is to just stick in the values of x and see what they look like. Yeah? Yeah? What else is there to do? So let's try that. So have to test, or have to check. X is equal to 2. And x is equal to 4. And it's an easy thing to forget, because it seems like you've got the answer, pretty much at this point, but you don't. You don't. The question asks for all x, and these guys here and here, we don't know. Yeah, we don't know. So we have to check. So let's just put them in. If we stick in x equals 2, so 4, x is equal to 2, then our series becomes the sum from n equals 1 to infinity of 2 minus 3, which is minus 1 to the n over n. Does that thing converge? Come on, does this thing converge? Give me thumbs up if you think yes, thumbs down if you think no. I appreciate the creative use of icons there. Tell me why. This is just alternating series. Alternating series test, these terms go down to 0, monotonically, the limit is 0, we're all set, yeah? So this converges. Okay, now we test for x is equal to 4. Put it into this series and we get this thing. Does this converge? No, it doesn't. It's just the power series. Sorry, it's just the harmonic series 1 over n does not converge. Cool. So we now have answered the question completely. We understand absolutely everything about when this series here converges, right? When we are x equals 2, right here, then it does converge. You know? When we are at 4, it does not converge. Yeah? So we have a complete answer for when this thing converges. And we erase some space and put this on. So series, let me say power series because it's a power series. For the interval 2 to 4, not including 4, right? And diverges otherwise. And that's the complete answer, right? There's nothing else. There's nothing else to be found out. The question was, for what values of x does this thing converge? It's exactly for these values of x. And if it's not these values of x, then it doesn't converge. Yeah? So we've totally nailed this down. Yeah? So on our picture here, which is a bit messy, at this point, it's like this. It's this half open interval, right? So this side is closed and this side is open. Are you comfortable with the terms open and closed when I talk about intervals? Is that familiar? Do a thumbs down if it's not. That completely does it. Let's go with what we did. We said, okay, let's just consider x to be fixed. Okay. Then we apply the ratio test, you know, and we get quite a lot of information. We find that when the limit is less than 1, it definitely converges. We write down what that means. That's the same as being strictly between 2 and 4. Yeah? We know when the limit's bigger than 1, it definitely diverges. That's the same as being either strictly bigger than 4 or strictly less than 2. Yeah? But there's two things still to check, and that's the numbers 2 and 4. And for those numbers, we just have to plug into the series. When you plug a number into the series, it's just a series. It's just a series. And we are now very good at determining whether or not series converge or otherwise. We spent a lot of time learning that. Yeah? So we have the tools to answer this question completely now. Yeah? We have the tools. Cool. Everybody good. Everybody happy. Yeah. So this is the main thing. We are given a power series which is given by the sum k is equal to 1 to infinity ak x minus a to the k. Does the book use a or a different letter? It uses ck, so let's follow the book. Don't have too many k's. Too many a's. Given a power series like this, there exists a number so there exist 3 possibilities. Possibilities. 1. The series does not converge at all, except when x equals a. only converges second possibility. The series converges for any x. And the third possibility, there exists R such that the series converges for any x such that mod x minus a is less than R and series diverges for mod x minus a is bigger than R. Okay, let's draw a picture. So the series is centered around a, some particular number. And there exists a radius R, like this, such that if we are strictly between a plus R and a minus R, then the series converges, then we are all good. And if we're strictly outside that, then it does not converge. Okay, so if we're strictly outside, it does not converge. Inside, it does converge. But there is nothing we know about the endpoints from this theorem. The endpoints, something else. And a way to think about this is that, morally speaking, there exists an R, but the R can be infinity and the R can be 0. So in this case, the R is 0. So if the R is 0, then the radius of convergence around the center is nothing. You have to be exactly on the center in order for the thing to converge. Yeah? And this is when R is infinity. In this case, you don't care how far you are away from the center. It doesn't matter. It's going to converge for every single x. Yeah? And in this case, there exists some finite R between 0 and infinity. Okay? That is how this theorem works. Okay. Leave at any time. I have a few more things to say on this topic. Okay? So, this is our main theorem that we're going to use. And we've already implicitly used it. And to see why this is true isn't particularly difficult, but it's somewhat beyond the scope of this course. All I want to say on this is, what did we do before? So, why could this be true? What we did before was we just considered this ratio when we considered this AN as being CK, or CN in this case, x minus a to the n. And then we just considered this thing. And it turned out to be just Cn plus 1 over Cn. If you just do the algebra, that's what you're going to get. What's what you're going to get, and this. So, if the limit as n goes to infinity of these terms, Cn plus 1 over Cn, existed, if it was some number L, then we have convergence if L x minus a is less than 1, right? Which is equivalent to saying that x minus a is less than 1 over L, and that thing is the number R. Yeah? That thing is the number R. Because if this limit exists, then this follows, which means this. So if x minus a is less than R, then this thing is less than 1, and therefore, so again, this thing is less than 1, and therefore we have convergence. If this is bigger than 1, then therefore this limit will be bigger than 1, and therefore it diverges. So it follows rather easily from the ratio test if we have that this limit exists. Okay? Many times, not many times, but it can happen that this limit doesn't exist, and then we have to replace this limit by something different called the limb sup, which is something you will learn about if you study more maths, which is something that always does exist. So if you are dealing with a series for which this is true, then this theorem is really straightforward. It is just the kind of thing we've been doing before. Okay? Yeah? Because let me just add to this. Because look, from this line, if we take the limit as n goes to infinity of an plus 1 over an, then if this limit exists and equals to L, it's just equal to L times x minus a. And that's the thing we want to be less than 1, right? So in order for this thing to converge, we need this thing, which is this thing, to be less than 1, which is equivalent to this thing. Yeah? So there's nothing really surprising or weird about this. There's nothing really odd. The only point which makes any difficulty is the fact that we don't always have that this limit exists. However, there is another mathematical concept that allows you to get around this. There's a concept of a limb sup, which always does exist, and the thing actually works. So this is not a particularly hard theorem to prove. It just comes down to the ratio test, essentially. Okay. So this R is called the radius of convergence. So okay, it's called the radius of convergence. And that's a number. Now, in all the questions where you're asked what the radius of convergence is, it'll be some number which is between 0 and infinity. So when we are discouraging you from thinking about infinity as a number, so informally, in this case where it always converges, you can think of the radius of convergence as being infinity, but don't put that down as an answer in a free response. Okay? Say it converges everywhere. Yeah? But this thing is also not the same as the interval of convergence. Another thing to emphasize. So the interval of convergence from this picture could be this. It could be this. It could be at these endpoints here, they both converge. Or it could be this. It could be this one doesn't converge and this one does. Or it could be this. Whoops. It converges here, but not here, or it could be this. All these things are possibilities for the interval of convergence. Right? And to find out which one of these possibilities is the case, we have to test the endpoints, just as we did before. So something to really nail down and have solidly in your head is that the radius of convergence is a number, the interval of convergence is a set of points. So when you ask for the interval convergence, it's asking for more information. It's asking for more information. Okay, I'm going to erase this. I'm going to do a table where we collate the information we found on the series we studied in terms of interval convergence and radius convergence, and then we'll be done for today. Okay. Well, it always has to be x to the k. That's the power series. This is a generalization of the polynomials. So, but the issue is what coefficients do we have in front so that the thing will always converge? What if we try something like that? Say it again. Well, if it's always going to converge, we need the coefficients to be going to 0 fast enough so that the thing will converge no matter what x we have. What if we do this? X to the k over k factorial. Yeah? What if we consider this? Yeah? So consider then that xk be x to the k over k factorial, ak plus 1 over 8k is just k factorial over k plus 1 factorial mod x, which is mod x over k plus 1, which tends to 0 no matter what value of x we have. Yeah? So, limit, let's write that in terms of limit of ak plus 1 of ak is equal to 0 for any x. So this series always converges. We don't care what the value of x is. It's always going to converge. Yeah? So this thing makes sense for every single x. This is a well-defined function for every single x. Yeah? Okay, let's create a table. I'm going to put the series here. We are going to put the radius of convergence here. And we're going to put the interval of convergence. Okay, let's think about the guys we studied already. What about this guy? The sum from k equals 0 to infinity x to the k. What is the radius of convergence? Think about the picture, right? So this is where the series is centered around. We have this r, where if we are strictly between a plus r and a minus r, we converge. And if we're strictly outside this, we diverge. Yeah? This stuff is good. Strictly outside, we are diverging. Yeah? And this r is the radius of convergence. So in this guy here, what is the a? Where is this series centered around? Where is it centered? 0, good. So what is the radius of convergence then? Look at the picture. Think about what we've learned about this thing. For what range of x does this thing converge? So radius of convergence is 1. Radius of convergence is 1, right? So in this case, the picture is we are centered on 0, and we are converging between 1 and minus 1, right? So the radius of convergence here is 1. Yeah? Do you all see that? Give me a thumbs up if yes. Thumbs down if no. Okay, so radius of convergence is 1. What's the interval of convergence of this thing? For what points does it actually converge? Not inclusive, right? If x equals 1, what happens? If x equals 1, we're just summing 1 forever, yeah? What about if x is minus 1? So does this converge if we have x is minus 1? No. So the interval of convergence is this thing. Everything strictly between 1 and minus 1. Yeah? Cool. What about this guy here? Sum k equals 1 to infinity, k factorial x to the k. What is the radius of convergence? And what is the interval of convergence? Firstly, what's the radius of convergence? Come on. Where is this series centered around? Yeah, the radius of convergence is 0. Yeah? And what's the interval of convergence? I just said it. It's just 0. Yeah? Just the set 0. Okay. What about this guy? What is the radius of convergence? 1. Very good. What's the interval of convergence? Good. Very good. Yeah? So we found out that this thing converges between 2 and 4. Whoops. It's centered around 3. Right? This is where it's centered. And the radius is 1. And we checked the endpoints and we found that it doesn't converge here, but it does converge here. Yeah? So the interval of convergence is something quite different from the radius of convergence, and it's something we have to work harder to find information about. Yeah? Cool. So with this picture in mind, where you think about where the series is centered, yeah? So it's centered when we have something like this. A series like this, sum k equals 1 to infinity, ck x minus a to the k. It's centered around a. That's what it means. So this is centered around 3. These guys are centered around 0. Yeah? So we think about where it's centered, and we think about what this r is, such that so long as we are between a plus r and a minus r, strictly between these two things, then that thing converges. That's the radius of convergence. Okay? And the interval of convergence is whatever points we find for which it actually converges. Okay, cool. These are the two main concepts you have to learn today. These are the things we'll be practicing, and you'll have homework problems about how to actually calculate. And it isn't particularly hard. It isn't particularly hard. Okay? It's just applying the ratio test and then testing the endpoints. All right. Everybody happy? Yeah? All right, so I've office hour now. Stick around if you have any questions. Otherwise, I will see you all on Friday. Have a